The world's most powerful rocket, SpaceX's Starship, is one of the engineering marvels of the 21st century. Standing 121 meters tall and capable of propelling 150 tons into low Earth orbit, the rocket is not only a symbol of technological advancement, but also a milestone in the history of human space exploration. Powered by a powerful Raptor engine, Starship uses a full flow stage combustion cycle, allowing for high performance with an impressive thrust to weight ratio. Methane being used as fuel for the Raptor engine is a major breakthrough in the rocket industry. Unlike traditional fuels such as kerosene or liquid hydrogen, methane is not only more efficient, but can also be produced from resources available on Mars. The Martian atmosphere is rich in carbon dioxide, which is the main ingredient for the Sabatier process, an efficient method of producing methane. In this chemical reaction, carbon dioxide is combined with hydrogen in the presence of a nickel catalyst at high temperatures and pressures. What makes carbon dioxide unique is that it has the highest freezing point of any gas in the Martian atmosphere. This allows us to extract carbon dioxide from the air simply by cooling it, a process known as reverse distillation. This process also condenses the carbon dioxide into a liquid. This opens up the possibility of long-term reusable space missions. The Raptor engine, which can produce up to 2,200 kilonewtons, 500,000 pounds on the ground, and 2,500 kilonewtons, 550,000 pounds in space, overcomes the major challenges of temperature and carbon buildup, delivering high performance and reliability. However, the biggest challenge is finding and exploiting water deposits on Mars to obtain the hydrogen needed for this process. SpaceX's Raptor engine needs to operate reliably over and over again, not just once. Methane helps solve one of these problems because it contains only one carbon molecule, reducing the likelihood of long-chain carbon soot particles forming. The Raptor engine operates by passing all of the fuel and oxidizer through the preburner. During this process, the fuel turbine pump runs the fuel-rich mixture, and the liquid oxygen turbine pump runs the oxygen-rich mixture. The excess fuel and oxygen from both sides are then combined in the combustion chamber in a gaseous state, where combustion is complete. However, the oxygen-rich mixture in the preburner can easily cause high combustion temperatures that can destroy the liquid oxygen turbine pump. SpaceX solved this problem by using a conventional closed-cycle engine, which only pushes a small portion of the fuel and oxidizer through the turbine pump. The Raptor's full-flow cycle sends all of its fuel and oxidizer through the turbine pump, which makes the temperature rise needed to run the turbine much lower, reducing the thermal load on the turbine blades. However, the hot, oxygen-rich gases escaping from the preburner still require special attention. During the SN8 test flight, a drop in fuel tank head pressure shifted the combustion process to an oxygen-rich environment, which reacted with the copper and melted the engine. A bright green copper flame appeared before the spacecraft went up in flames. To solve this problem, SpaceX cast Raptor components from Inconel, a nickel-chromium alloy with high heat and oxidation resistance. The engine has proven capable of propelling a giant rocket into orbit, but there is still work to be done to realize SpaceX's grand vision. The giant booster still needs to land successfully. During the IFT-3 test, the Super Heavy booster fired its engines for Starship's first landing, but disengaged unplanned at an altitude of 462 meters. During the initial supersonic descent, everything seemed stable. But when the engine was reignited while flying through the altocumulus cloud layer, the rocket appeared to be hit by a strong wind shear, destabilizing it and causing it to break apart. The lattice blades can be seen struggling to return to a stable position before exploding at 462 meters. While the wind shear was predictable, the booster appeared to be moving faster than expected, affecting stability and control. With IFT-4, SpaceX will likely slow down more rapidly to improve stability and control. Starship and its Super Heavy booster are moving closer to full reusability, with plans to land and reuse them right on the launch pad. This will not only reduce costs, but also increase the ability to perform missions repeatedly and quickly. The spacecraft's heavy-lift rocket, which will be capable of carrying a 150-ton payload to low Earth orbit, will have no landing legs and will be caught by a mechanical arm and flown back to the original launch pad, eliminating the need for heavy landing legs and reducing the chance of the Raptor engine destroying the landing pad upon landing. Beyond launching heavy payloads, SpaceX plans to develop different variants of Starship for manned, unmanned, and special missions, such as to the moon. These variants will have different designs and features, suitable for each specific type of mission. For example, the Starship variant for lunar missions will be equipped with a dedicated landing system, while the variant for Mars exploration will be capable of producing its own fuel from CO2 and water on the surface of the red planet. SpaceX has discussed plans for a second stage variant designed to act as an orbital fuel depot. This would allow other spacecraft to refuel while in orbit, extending their range and capabilities. The most widely used variant is the one specifically designed to launch Starlink. With a flat panel design, 60 Starlink satellites can fit into the Falcon 9's 5.2-meter wide payload bay, maximizing its low Earth orbit capabilities. SpaceX could achieve more with Starship's larger payload capacity, allowing it to launch larger Starlink variants with larger antennas, providing stronger signals to support reliable cellular networks in rural areas. In the future, Starship will not only be a means of transportation, but also a platform for the development of new space telescopes, providing the ability to observe and explore the universe in more detail and precision. For example, one of SpaceX's ambitious plans is to develop a new space telescope 10 times the size of the Hubble telescope, allowing it to observe the deepest regions of the universe and search for signs of life on other planets.